a chip that reportedly runs 100 billion parameter artificial intelligence models, the class that powers large language systems, at a 5 nanometer process node with no license from any foreign company. No royalty, no terms of service a trade lawyer can reach. That chip obeys a language nobody owns. Before you file this under Chinese state hype, the architecture underneath that chip is not a Chinese invention, and it is not a secret. It is an open standard developed at Berkeley that every company in the world can read, fork, and implement. China's bet is not that it invented something new. It is that the open lane reaches far enough to matter. By the end of this, you will understand why the instruction set is the most underleveraged choke point in the export control debate, what RISC-V actually changes about that choke point, and what the XuanTie C950 tells us about how far the open lane now reaches. The instruction set architecture sits below every operating system, every compiler, every application ever written. Whoever controls it has a hand on the deepest switch in computing. Most of the world's chips pass through two tolled gates, ARM and x86. One revocation letter, properly routed through the right jurisdiction, is all it takes to scramble an entire national chip program. This is not a story about one processor. It is about who is allowed to set the rules that every chip, everywhere, must obey, and about what happens when one country decides to help make those rules free. So start with the rules themselves. An instruction set architecture is not the chip. It is the contract the chip signs with every piece of software ever written for it. Think of it as the gauge of a railway track. Every train, every piece of software, is built to fit one gauge. A compiler targeting ARM produces instructions in ARM's format. An operating system tuned for x86 speaks x86. Change the gauge without warning, and every train on that network stops running. A nation that does not own its gauge standard can be told, without warning, that its trains no longer fit the tracks the rest of the world uses. Can you just rewrite the software? In principle, yes. In practice, the installed base of ARM compiled code across embedded systems, smartphones, and servers represents decades of developer output. No country rewrites that in a budget cycle. The cost of switching is so high that the instruction set owner gains permanent leverage, not because chips are physically unique, but because the software stack is. And the entity that owns the gauge does not have to do anything dramatic to exercise that leverage. It just has to make the chip designer uncertain. That uncertainty became visible in 2020. ARM Holdings is incorporated in the United Kingdom and majority owned by SoftBank of Japan. But ARM uses United States origin technology in its architecture, and that fact places advanced ARM licenses and design support under United States export control jurisdiction. When the United States added Huawei to its entity list in 2020, ARM was required to pause new architectural licenses and halt design assistance to Huawei's chip division, HiSilicon. ARM later clarified that some existing agreements could continue under a more complex set of rules, and the situation evolved. The full picture was never a clean cutoff, but that is almost beside the point. The episode proved the mechanism. A foreign body could be forced to hesitate, restructure, and negotiate its relationships around United States technology jurisdiction. HiSilicon's Kirin chips were ARM-based. The design pipeline faced immediate uncertainty. That uncertainty alone forces every serious national chip program to price in the risk. You do not need the lever to be pulled all the way down to change how engineers plan around it. The question that followed, in boardrooms and government offices and research labs, was whether there existed a gauge standard that no single jurisdiction could reach. There is one. and it was built by academics to teach undergraduates. RISC-V originated at the University of California, Berkeley, with its first formal publication in 2011. It is an instruction set architecture published under open licenses. No royalty, no permission required from any national authority to implement it. But here is the detail that changes its strategic weight. RISC-V International, the body that governs the specification, is a Swiss non-profit. That redomicile happened in 2019 and 2020, and the stated rationale was explicit. Switzerland's legal jurisdiction sits outside the reach of United States export control rules as applied to the specification itself. The floor was placed on neutral ground deliberately. The organization's membership spans over 4,000 entities across more than 70 countries, according to reported counts from RISC-V International. That membership includes Qualcomm, Google, Western Digital, and NVIDIA, companies at the center of the United States semiconductor industry. It includes European chip makers and research institutions. And China is reported to have among the largest national contributor and member cohorts of any country within the organization, though the exact ranking is not confirmed in the available record. No single member, including Berkeley, can revoke another member's right to implement the specification. That is what makes the floor structurally different from a proprietary ceiling. RISC-V International is something like a land treaty signed on neutral ground. The territory it protects is the specification itself, and no single signatory can later fence it off. There is one honest caveat here worth holding on to. The specification is free. The tools you use to compile for it, certain commercial electronic design automation software, some of the libraries, those sit on a separate layer with separate legal exposure. The floor is free. Not everything above the floor is equally free. Keep that in mind, because the story goes there. First, the evidence for how high the floor now reaches. Alibaba's semiconductor design division, called T-Head, which operates under the company's research arm, has reported a RISC-V core design called the XuanTie C950, fabricated at a 5 nanometer process node. 5 nanometer is the same process generation used in Apple's A15 and comparable advanced chips released in 2021 and 2022. To be precise, these node names are process generation labels, not literal physical measurements of transistor features. But as a generational comparison, 5 nanometer places the C950 in the same fabrication tier as the chips at the center of the current consumer and compute frontier. T-Head has further claimed the C950 can run inference on models with 100 billion parameters. To make that number feel real, 100 billion parameters is the rough scale of the model class that powers large language systems, not a voice assistant or a search autocomplete, but the class of compute that made the current artificial intelligence wave visible to the public. Running inference at that scale requires high memory bandwidth, large on-chip storage, and sophisticated interconnect between processing elements. It is not a benchmark you can reach with a chip designed for embedded sensors or edge controllers. Think of parameter count as the weight of the model, how much the chip has to hold in mind at once. Getting a RISC-V core to carry that load at 5 nanometers is the equivalent of building a high-speed rail line on a track gauge that until recently only ran local commuter trains. The gauge has not changed. The engineering above it has. Now, hold the honest limit beside that claim. T-Head's result is company reported. The benchmark conditions and methodology have not been independently validated in the available record. The production status of the C950, whether it represents a prototype, an engineering sample, or volume production, is not confirmed. The foundry that fabricated it at 5 nanometers is not identified in the available record. These are not minor footnotes. They are the questions that separate a directional signal from a verified result. The claim is worth holding appropriately. It tells us that T-Head believes RISC-V can be positioned at the frontier of compute, and that they have committed actual silicon to that argument. Whether the result holds under independent scrutiny is exactly the question that should be asked, and it has not been answered yet. What the C950 exposes, though, is where the honest remaining wall actually stands. Because reaching the frontier with the instruction set architecture is only part of the problem. The license risk is genuinely removed by RISC-V. What is not removed is the ecosystem. ARM's architecture dates to 1985. 30-plus years of compiler back-end optimization have been baked into the LLVM and GCC compiler toolchains. Decades of architecture-specific tuning live inside operating system kernels. In libraries developers reach for automatically in the shorthand that makes code faster to write and faster to run. RISC-V has active LLVM and GCC backends. Frameworks like PyTorch and TensorFlow have RISC-V support in active development. But active development is not the same as ARM-level maturity, and practitioners in the field describe RISC-V's general-purpose compute ecosystem as running a few years behind. Think of it this way. The instruction set is the grammar of a language. RISC-V has published its grammar for free, and anyone can use it. ARM's dictionary, the accumulated idioms, the developer shortcuts, the optimizations that run quietly inside every compiled binary, took 30 years to write. You can learn the grammar in a year. The dictionary takes longer. So is RISC-V just hype? That is the wrong question, and it collapses a more interesting distinction. The instruction set layer genuinely removes the license choke point. The ecosystem layer genuinely lags. Both things are true simultaneously, and the strategic bet does not require denying either one. The bet is more specific than that. New artificial intelligence frameworks being built from scratch for new accelerators do not carry 30 years of ARM-specific shortcuts baked in. A developer writing a fresh inference framework for a new RISC-V accelerator does not inherit ARM's accumulated advantage. They start level. The switching cost that gives ARM its leverage in legacy compute largely disappears in workloads that have no legacy. And increasingly, the workloads that define the frontier are exactly the ones being written fresh. That is why China's position in this story is not what it might first appear. China is not alone in betting on RISC-V, and that is precisely the point. RISC-V's credibility as a floor comes from its international breadth. Western semiconductor companies, European chipmakers, American universities, and Chinese firms all contribute to the same specification. China's strategy is to be among the most capable builders on a floor it helped make genuinely international, not to own the floor unilaterally. It does not need to own RISC-V. It needs to ensure nobody else can close it. An open floor governed by Swiss non-profit rules is structurally harder to weaponize than a proprietary architecture routed through United States technology jurisdiction. The fact that Qualcomm and Google also sit on that same foundation does not undercut China's independence. It reinforces it. The more international the contributor base, the less any single government can credibly threaten the specification itself. China is not trying to beat ARM at its own game. It is helping build a floor no single nation can own, and then racing to be the best builder on top of it. Here is my honest read. The triumphalist version, that China has solved the instruction set problem and is pulling ahead, overstates what one company's reported benchmark proves. The C950 is a directional signal, not a verified deployment at scale. The dismissive version, that RISC-V is a teaching tool for undergraduates and this is all noise, ignores what a reported 5 nanometer artificial intelligence capable core signals about how far the open lane now reaches. Neither extreme holds. The reading that neither side states cleanly. The floor has been raised to a level that genuinely matters. The instruction set chokepoint is a solved problem at the specification layer. The chokepoint has moved one floor up to the compiler depth, the library breadth, the accumulated developer trust that ARM built over decades. That is a harder problem than the instruction set was, and it is more tractable in new artificial intelligence workloads than it ever was in general-purpose compute. Because in general-purpose compute, the legacy runs deep. In frontier artificial intelligence frameworks, the page is closer to blank. That is where the actual contest is being run. Here is what I want your honest read on. The ecosystem gap is real. RISC-V's compiler depth and library breadth trail ARMs by years in general-purpose compute. But new artificial intelligence frameworks are being written from scratch, which means they carry none of ARM's inherited advantage. Does the ecosystem gap close faster in artificial intelligence workloads than it ever could in general-purpose compute? And does it close fast enough to matter before the window narrows? I want your answer in the comments, and I want the reasoning, not just the verdict. If you want to follow whether the C950's reported result holds up under independent scrutiny, and what comes next in the layer above the instruction set, subscribe. That is exactly what this channel tracks as it unfolds. A chip that obeys a language nobody owns. The floor it stands on was built by hundreds of companies across dozens of countries. Nobody can pull it out from under it now.